So welcome back, everyone, to the course, and we discussed last time beginnings of our ideas for a new proof, well, an exponential improvement in the Ramsey numbers, and in particular a proof that can work for the multicolored version as well. And we said there'll be a particular geometric lemma which is absolutely central to the argument. Maybe I'll just give a quick reminder of maybe the idea of the approach. And so just to make it look a little bit more believable, this geometric lemma is useful. So we know we're going to have a set X of some candidate vertices that can join the books that we plan to build. I'll do the picture just with two colors, so it seems a bit easier to draw. So you're going to try and be building a red cleat T1, and you'll have a set Y1 that just joins in red to T1. These are red as well. And you're going to have another book with T2, Y2. And we said in a given step, well, a normal step, a color step, you hope to take a vertex in X. And if you can do a red step, you add X to T1, and then you have to restrict both X and Y1 to be the red neighborhood of this little vertex, if you do that step. And what's the potential problem? The potential problem is there's some vertex in here who has few neighbors in common with this new Y1 set. And that will lower your degree condition you have. Remember, instead of density, it's a similar idea to density. Usually we talk about density in the previous argument. Now we're actually going to ask for a minimum degree condition. So you could say let P1 be the minimum of the density in color 1 from X to Y1. And you want to do a step where either this minimum degree type condition is maintained, or at least it doesn't get very much worse. So you want that after you maybe just lose, you either have P1 or P1 minus. There'll be some decision to make about how you choose the alphas, but that's sort of a detail we want to come on to. Now, what's the problem? It could be that for a given X, he has some red neighbors, they're all bad for him, to his red neighborhood, and he has some blue neighbors, and they're all bad to his blue neighborhood. And then you have nowhere to go. So what you'd like is that there's some positive proportion of the pairs in here which are kind of good both ways. If you have some positive proportion that are good both ways, you can find a vertex with positive proportion of its neighbors are good both ways, and you'll be able to do a color set. So this will maybe come back to at the end if we have time. So we want some sort of statement that says, again, being good, we can encode in terms of inner product. We can encode the neighborhood as a vector. You basically take the indicator function, maybe rebalance, so that inner product 0 corresponds to sort of having the intersection you ought to. And basically, you want to find lots of pairs whose inner product is not too negative. Say at least minus alpha. We could have said at least minus 1, because the difference there is just renormalization. Right. Okay, so you could say what you're really doing is for every pair here, you have an inner product of that pair, okay, in two different copies of RD. And so you can say, what's the inner product of that pair under one function from X to RD? And you have lots of different answers, and you can look at their inner product with respect to another mapping, sigma 2. and it'll give you a bunch of points in the plane. And what we're saying is we want at least 100th of these points, say, to be bigger than -1 in both coordinates. We just want some weight here. And strangely, this is not always possible. Well, of course, it's not always possible if you put arbitrary points down, because you could just put points over here. But you might hope you have some extra structure on the set of points because of where they come from. Because they come from being inner products of pairs in two different ways. And it turns out you can say something. You can say either you have some weight here, or the distribution is kind of strange in that it has some very large values. Now, if you go to a big distance, maybe you expect things to go away and fall off like a Gaussian, which would be like e to the minus x squared. And we're going to say either you get the property you want, or the fall off is just like e to the minus root x. In other words, we find a proportion of pairs in the tail, which is maybe much bigger than you'd expect. Sort of randoms. But maybe I should just state the geometric lemma now, because we're basically doing it. But it's kind of clear the way this relates to the original problem. This thing we're going to have to come back to, of course. But I thought, otherwise, if I state the lemma without saying anything, it looks a bit like, why are we doing this? So let's just say let S be a finite set. I guess S is really our X in the application. Technically, it could be an infinite set, but if you do finite set, and all of the expected values that go are obviously well defined, which is easier to state finite set. And we'll have U and U primed, I, D random variables taking values in S. I mean, you can think of these as two uniforms, really, but anyway, it works as the idea of values in S. And what we're going to do is we're going to consider, basically for each point in S, like we did here, we can consider different functions from S into RD. So let's sigma 1, we'll do 3 functions, because we're doing the 3-color version of the proof, really. I didn't think about doing the results today for any number of colors, these 3 or whatever. But I thought, no, we're kind of doing the 3-color proofs. Let's just do the 3 colors. So we're going to have 3 functions from S into RD. And these are arbitrary functions. Okay, so the event we sort of like, that E be the event that if I look at the inner products of U, I, so sigma I of U and sigma I of U primed, we like when this isn't too small. We like when this is at least -1. So that E be the event that for all I, well, just one, it's 1, 2, or 3 in this case, you always have good inner product. That's kind of saying you have some, it's the event of having points in this part, which is a good one. And what's the conclusion of the geometric lemma? It's going to be either the probability of this event E is at least 1 over 100, or you get this weird tail head. And that is stated as there exists lambda at least 0, and the sum J, which could be 1, 2, or 3, in direction J, you have lots of points which are quite large. So probability that the inner product of sigma JU, sigma JV, those are U prime, sorry, is at least lambda, and the event E, in fact, is at least, and now it's going to be at least an exponential minus 12 lambda to root lambda, shouldn't it? Root lambda. At least exponential of minus 12 root lambda minus 12. So I realize I'm going to have a bit of a problem because because I've used up an entire code stating it. So in a minute, maybe I'll have to do like a very small statement for this. Otherwise, it's just taking up all our space. But maybe first I'll mention how we're going to prove this lemma, which is not at all obvious. It's sort of interesting. It's a completely general statement. You've got any finite set, any three functions, and somehow you're saying something about the geometry of the inner products. Either you have a decent probability of all of the inner products being at least -1, or in at least one of them, you have some good probability of large. Now, you should, I know this is probability. It's probability because I said random variables. You can't just think of these as two uniforms, right? And then when it says probability, it's really just what, because you're picking U and U prime, it's sort of what proportion of pairs does this happen? So you could just think it's saying for at least 100 of the pairs, you get all of these three inner products at least -1, or there's at least disproportionate of pairs, such that in J, the inner product is large, and the other two are at least -1 as well. So let's see the idea. So it's one of those things where I can name the ideas, and it doesn't mean it's super intuitive. Obviously, you should have thought of this, okay? Because that sometimes happens with proofs. You're like, obviously, this is the right thing to do. Well, I'll write them down, and then you can tell me if you would have thought these are the obvious things to do. First thing is these inner products have nice properties when you take the expected value. In particular, they have non-negativity properties. And these non-negativity properties also hold when you do higher moments and even mixed moments. Okay? So the first idea is show moments and mixed moments of these guys are non-negative. So it's just going to be like expected value of this with 1 times this with 2. Or this with 1 to the power 6 times this with 2 to the power 4. So that's sort of a mixed moment. The next one, now this is the one you're going to tell me is super obvious, is we consider the function f of x1, x2, x3. You should think of these three directions, sort of in my picture, I had this two-dimensional picture with which represents the inner products of the directions. This is just the same thing, but now with 3 dimensions. And I'm going to consider a certain function on those 2 dimensions, which is naturally the sum I equals 1 up to 3, xi, times the product over the other 2, j different from I, of 2 plus cosh of root xj. I told you, did that feel good? Now, as I said, not all times when someone tells you the ideas, you think that was a very obvious idea. But this turns out to be a useful function to think about. Yes, what are the properties of f? This is basically actually what we're going to spend the next, first part of the class doing, is proving the properties of f. Well, the properties that are most essential are that if you do its expansion in the same way, your exponential has this expansion, Taylor series, whatever it is, this does too. And even when you consider the sort of multivariate version, all of the coefficients are non-negative. So it will follow from the mixed moments that the expected value of f of the inner product things is non-negative as well. We'll state this better in a minute, but you can pass this mixed moment property to non-negativity at f of the inner product. And then we need some bounds on f. In particular, if any of them is very negative, then f gives you something negative. And on the positive side, its growth is at most like e to the root x, which is related to the e to the power. So, yeah, maybe I'll try and do a very brief version of the geometric lemma above, because it's useful to have around, but we can't have it taking up a whole board. And then we'll go on to, well, the first thing we're going to have to do, if this proof involves this crazy function f, we're going to have to think a bit about cosh of root x, 2 plus cosh of root x, whatever. We've come up with a silly function, we're going to have to say something about it. Okay, so even for the point of the video, let me just pause and read. Yeah, good, let's go. And now we have a geometric lemma much more reasonable size. Just do the same thing, squeeze it up there at the top. So now we have space to think about what are the properties of f, this funny function. And of course, f is made out of like cosh of root x. So we need to think about those functions, properties of f. So the first thing is, if you take cosh of square root x, that's just e to the root x plus e to the minus root x over 2. And this has an expansion. Basically, the terms that were the even terms survive. The terms where the odd terms cancel. But because we're doing it in root x, it actually is, you get 1 plus x over 2 factorial plus x squared over 4 factorial plus x cubed over 6 factorial, and so on. So that's the expansion we're talking about. So already we can notice all the coefficients are non-negative, or positive. Obviously, the same is true if I do 2 plus cosh root x. Still the case, all the coefficients are non-negative. So in particular, this implies, say, let's call it lemma 1. I know I may have used lemma numbers before, but let's just start fresh today. So lemma 1 is all coefficients in expansion of f are non-negative. So that would be like a multivariate expansion, right? Because f has an x1, an x2, and an x3. But you get them by multiplying like x1 times a copy of this and x2, copy of x2. All of the multivariate polynomial terms have non-negative coefficients. So that's an important property. We also need to understand what values f takes. And in a minute we'll say a lemma, which is actually about the values of f, but let's start with some observations. Well, the first is if you have a negative value of x, then apparently the cosh of root x is the same as cosine of root of minus x, which is always in minus 1, 1, of course. And that's all we need to know about it, actually. When x is negative, we're just going to use the answer lies in its interval. And that implies, in particular, when you look at 2 plus cosh of root x for x negative, that always belongs to the interval 1, 3. And when x is positive, what can we say? For x at least 0, we have Well, there's the following lower bounds and upper bounds. X is the lower bound for 2 plus cosh of root x. And 3e to the root x is always an upper bound. So these things are easily checked. It's also maybe worth noting if you take any x, positive or negative, you can have the same upper bound here. I guess even, yeah, I guess even both of them, right? But in particular, we have the upper bound, and what I'm going to do is put x plus. X plus is the positive part of x. In other words, it gives you x if x is positive, it gives you 0 if x is negative. Now let's state the lemma about values of f. Lemma 2 of x1, x2, x3 is at most. So we'll actually give 3 bounds depending on these numbers, depending on the maximum and minimum stuff. If the maximum of the 3 is positive, then you have an upper bound which is, no, remember, I think it's 3 to the 4, and then you have e to the sum of the square root xi, like so x1 positive plus root x2 positive plus root of x3 positive. We've got more space if I'm using. This is if the maximum is positive. I mean, maybe this one actually always is true, but anyway, we're going to use it in this. Actually, if the maximum is negative, meaning they're all negative, then you can use 0 as that bound. And perhaps most importantly, there's this strange property. If any one of these is very small, then you can say f is less than -1, or most minus 1. And this is if the min of the 3 is at most -9. So it's somehow an interesting function. So I guess we should prove lemma 2, because it's not so obvious. I'm going to say the middle case is obvious. Perhaps I should squeeze in. I'll squeeze in the definition of x again. You sum xi, you do the products j different from I, 2 plus cosh of root. So I'm going to say the middle case is easy because if they're all negative, then every term is negative. This guy's always positive. There's always at least one. And all terms are negative. So middle case is easy. So let's go to the case, let the maximum be positive. Right. So all we do is we use that. Maybe I should do this. This is even true. This last one. Basically, if you look at a particular term of f, this x is at most what it would be if you put a 2 plus cos root x, right? Because x is at most 2 plus cos root x. So actually, f is less than or equal to summing 3 times this product, the way you include everyone. Right? You could just include them in the products, and it would only get bigger. And so it's at most 3 times doing the product of all 3 guys. But all of them individually are at most 3 times the square root of their positive number. So I don't know if, I mean, I kind of just said it, but I guess what I'm saying then, should we start with that? I'm saying this is less than or equal to the sum I equals 1 up to 3 of the product of cosh, 2 plus cosh square root xi, and then that's the most 3 because you're summing 3 terms, and the product of each term is like e to the is bounded above by 3 e to the root xi positive part. Okay. And it's clear this gives you exactly 3 to the 4 e to the sum. Those. So let's go to the weird case where we're making a strange claim that even one of them being small is enough to guarantee the whole answer is small. So if the min of x is at most minus 9, well, the log x1 is at most minus 9. It's a completely symmetric definition. And so what do we have? Okay, f of x equals, and what I'm going to do, and look at the definition, again we'll say, well, we could consider the product of everybody, but now we'll do it more carefully. If you consider the product of everybody, then you can put the product outside the sum, and you can see that f is actually the product of all of the 2 plus cosh root xi times the sum. And now you want to rebalance. So really, you're supposed to have xi over 2 plus cosh. Right. It's the same thing as saying, it's basically saying let's multiply and divide by 2 plus cosh root xi. If you multiply it by it, you have the product of now over 3. You divide by it, you put it in underneath there in the term. The sum. And then if you have the full product, you can just put it outside the sum. Right, so we want to show this guy is less than or equal to minus 1. Observation, this product in front is at least 1, because this 2 plus cosh root x is always at least 1. So it's sufficient to prove that this guy here is less than or equal to minus 1. And what do we have? The first term of this, the first term is the one where x1 is less than minus 9. Also, this guy in the denominators at most 3 when you're negative. So the first contribution is at most minus 3. And all we need to observe now is that each other contribution is at most plus 1. That's because if x is negative, well, the contribution is negative. If x is positive, well, x is less than or equal to the denominator. So it's certainly at most minus 3 plus 1, which is minus 1. Okay, so it's just a technical thing, silly little thing, but it does give us what we want. So we've got more information. I think what I might do now is sort of summarize the information just here, and then we can clear the boards again and have more space. So we've summarized lemma 1 up here, just the fact that we've written with all the coefficients on negative, and lemma 2 I ended up leaving up here. So let's get on to the other part we need to do, which was part of the plan, which was something to do with moments and mixed moments. So maybe we can just jump straight in and put a lemma down about mixed moments. So this can be lemma 3. So maybe I don't need to write it again. We're in the same setting. S is a finite set. We'll put S finite. And U and U primed are IAD RVs. I know you can just put it in S, right? You know, taking values in S. And again, we have three functions, sigma 1, sigma 2, sigma 3, from S to some Euclidean space. I think it's just the sum in a product space, really. We don't really use much else about it. But anyway, it's in a Euclidean space. Then we want, so the statement will be all of the mixed moments are non-negative. So then for all integers, you have L1, L2, L3, non-negative. We have the expected value of, okay, first inner products, sigma 1 of U, sigma 1 of U primed, to be L1, second inner product, sigma 2 of U, sigma 2 of U primed, to be L2, and third inner product, sigma 3 of U, sigma 3 of U primed, to the L3. This is always non-negative. Yeah, it's interesting. So there is the proof in some sense is fairly formal. I think it's almost easier or better or something to do a couple of very simple cases just so we realize that there's something very elementary going on here. Because you can say the proof, but it all sounds much more formal when you do it in complete generality. So let's do as examples. Well, the first example would have to be L1 is 1, and L2 and L3 is 0, right? Maybe you already believe this case, anyway. And let's just to simplify that, U and U prime be uniform in S, just so I don't. And then I can actually write out the proof with summation instead of expectation. I don't know if it's better. But in this case, what happens is just about the expected value of sigma 1 U in a product, sigma 1 U primed. And you can, because the selection is uniform, you can just do 1 over the size of S squared and sum over UV and assume U is equal to U. It could be U prime, as soon as write UV. And then what you're summing the answer, sigma 1 of U, sigma 1 of V in the product. And now, there's an obvious reason why this is non-negative. Just the linearity of the inner product means you can stick the summation inside and sum the first term over U, sigma 1 of U, and the second term over V, sigma 1 of V. But remember, you're summing over the same set in both cases, so these two things are equal. So you have an inner product of something with itself. So, non-negative. Perhaps we could do just one more case, and because I think this gives the idea of what the general thing is. So if you take L1 and L2 to be 1, the L3 is still 0. Again, we'll carry on with uniform. So now we're doing expected value of the product, the inner product, U1, sigma 1 U's, sigma 1 U prime. Is that times the inner product when you use sigma 2. Maybe it's a bit less obvious that this should always be non-negative. There's something going on, there's two different inner products. But you remember, you're still just using two elements of S, right? So it's still 1 over S squared, the sum over UV. And just to be, I don't know if this, anyway, just to be more pedantic about it, I'm going to write out the inner product as like a sum over I. And what do you got? You've got sigma 1 of U in position I sigma 1 of V in position I, and the other inner product, sum over J, sigma 2 of U in position J, sigma 2 of V in position J. Okay. But then what you can do is swap the summation. So we'll sum over Ij here at the start, and we'll collect together the terms of U with U, in terms of V with V. You have sum over U, sigma 1U I, sigma 2U J, and you have the sum over V, sigma 1V I, sigma 2V J. And what you notice is really, okay, it's like this is indexed by I and J. So this is basically like a matrix, Aij. Right? You basically just consider this as giving you a different answer for every I and J, the value of the sum. But U and V is summing over the same thing. So this gives you the same for every I and J, this gives you the same thing as that one. And then really what you're doing is an inner product of two matrices, where you consider the inner product sort of entry-wise. You know, just summing over every entry in the matrix, what is it in this one times what is in this one. And then it's easy to see, it's just an inner product again, and so it's at least zero. I mean, if you prefer, you could say, instead of thinking of it as a matrix, you can think of it as a vector of both products in this way. So why was it useful to see this second one? Actually, this second one is already showing us what's going to happen in J. So it's one of those things where I did write out the proof here, because I thought maybe I presented them. But I'm starting to think I won't bother to present them, because it's not super interesting. I mean, it is, in a way, it's interesting, because, you know, there's something unexpected about it, perhaps. But when you see that inside, it's just doing this. Anyway, what happens in general is, I suppose, for every U, you can, yeah, basically this ends up producing a thing indexed by I and J, because you have these two terms of one. In general, it would produce a tensor, like this big box of numbers, where the dimension of that tensor is the sum of the L's. So you can have, I guess in general, the proof, you have a tensor, and for each U, remember, for a given U, you can have a matrix like this. This is really like summing of the matrices. For each U, you can have a tensor, mu, indexed by a vector I. This is where the vector I lives in S to the L, L being the sum of the three L's. And basically, we have to define this tensor by, you want to include the, right, you do mu of some sequence, I1 up to IL. In that particular entry, what you do, you multiply the sigma sigma 1 of U in I1 yeah, basically you use sigma 1 L1 times until you get up to would be I L1, and then you use sigma 2 L2 times, and use sigma 3 L 3 times. Okay. And it's one of those things which happens about. I should give it a fancy version, which is what we put in the paper. Somehow the fancy version, either you know the algebra already, and it doesn't have some trivial algebra fact, or you don't know it, and then you haven't. That's it. But then you can calculate the thing we actually want, which is this mixed moment. Let's say dot dot, press the mixed moment. L1, L2, L3. It's the same as we did in this case. Instead of writing the inner product, you can write sum over I1. And so you're going to have sum over I1 up to sum over IL. You know, writing out the inner product in all these cases. And you do it for U and U primed, but then you can just separate out the terms of U and the terms of U prime, exactly as you did with U and V down there, and take the summation outside, and you get the expected value of this tensor with U and the tensor for U primed. And then by independence of the random variables, you have product, and once you use the product, then you know now the entries are the same, right? Because U and U prime have the same distribution. So this is just like an inner product again. So it's okay, so that's at least one way of writing it. Another way is to say you're generating this tensor by doing an outer product of all the results, and then there's a algebraic fact relating the inner product and the outer product. But I don't know, to all intents and purposes, really, it's just the same proof as that one where you notice you produced a matrix in each index y and j, and then the inner product is really really becomes an inner product of those matrices entry-wise. In this case, it becomes like an inner product of these tensors entry-wise. And so, for this reason, is not negative. So we basically now have all the pieces we need to prove the geometric lemma. Let's maybe just combine lemma 1 and lemma 3 into one statement now, because lemma 1 is saying we have an expression for f as a multivariate polynomial or series, whatever, with all of the coefficients non-negative. And lemma 3 is saying whenever you do an inner product where the power is, well, any mixed moment calculation with these inner products, it always gives you something non-zero. Well, that's going to carry over to f. Perhaps before doing that, I should maybe give me some of the order. Okay, I'm going to start the proof of the geometric lemma here then. And in a minute, once we've got first definition, we can clear up some of this stuff. So proof of the geometric lemma. So first what we're going to do, we're going to I mean, what we're clearly going to do, we're obviously going to want to use, is this function f, but with the entries being somehow these guys. There's actually a technical reason why it's better to use zi being 9 times the corresponding inner product. So this is the random variable as well. Get it from the inner product. We take zi to be 9 times the inner product of sigma I of u primes. This is for all i's 1, 2, 3. You can probably guess where the 9 comes in. because the eventual theorem has an event which is related to everything being at least -1, whereas this has a different behavior if everything is bigger than -9. That's the only reason you have a 9. Okay. So, as the Zi is just a fixed multiple like 9 of each of these guys. So clearly from lemma 3, this also holds with the Z guys. Because I've just multiplied by 9 3 times. Still not negative. And now we use that you have a series expression for f with all the coefficients non-negative. So when you do expected value of f of these Z guys, Z1, Z2, Z3, then you could do it by just summing the terms of the series, and the expected value of each of them is non-negative. So we have the expected value of f of, I'll put vector Z, right? It just means Z1, Z2, Z3 is non-negative. That follows with lemma 1, lemma 3, and so now we can get rid of lemma 3. And now basically the idea would be to combine this observation with our bounds on f and see what happens. So we now have what? We have 0. Now before I do that, I think we should note one thing. Note, what is the event E? E is the event that all of the inner products are at least -1. Was the Z's are just 9 times bigger. So it's the event that what? The minimum of the Z's is at least -9. So it's just useful to know that event. And so, for example, on E complement, the function will be less than or equal to -1. Right, so now, what do we have? 0 is less than or equal to the expected value, is less than or equal to, and now as well use our lemma 2, right? If you're at E complement, then one of them is less than or equal to -9, and so the value you get here is at most -1. So we get a minus the probability of E complement. If this doesn't happen, but still the maximum is at most 0, then you get a most 0. So the only other contribution comes from the case where the maximum is at least 0, and therefore you can use this as the upper bound for f. So let me put that upper bound for f in the remaining case, which is 3 to the 4, expected value. And we'll actually use something a little bit worse than this. I'll just use, instead of giving the sum, I'll just use the maximum 3 times. So e to the 3, to use roots capital N. Maybe I'll use a different color for the middle. So let's stick it in here. Capital N is the max of the entries of Z. I can still put in here an indicator function of the event E and the event N is positive. Because if you're in E complement, we've already said we can use the upper bound -1. So it's only if you're not, if you're not, if you're in E complement, you can -1. So it's only if you're in E that you would possibly use this bound. And so in that case, your 3 to the 4 expected value of E to the 3 root n, that's an upper bound. And you can put the indicator function that you have E and the maximum is possible. Right. So the thing that happens now is there's sort of an exercise in integration. And because I'm not very good at these things, I mean, I have understood it because I had to, but I feel like I'm going to explain it because to me it wasn't very obvious before. So I'm going to go over here and talk a bit about doing integration. Let's just look at this thing inside. Observe. This thing inside is random variable. E to the 3 root n. I guess I can throw in the indicator function as well. And what happens if m is 0? Then e to the 3 root n gives you 1, right? E to the 0 is 1. And so in that case, you still have the indicator function. So this is actually equal to the indicator function plus, well, you know, it's just doing a derivative, right? If I have a certain value, I can write it as the start point plus an integral of a derivative. So plus the integral. Now you'd think I would write 0 up to n. I actually write 0 to infinity and then just put an indicator function that m is at least x. So it's kind of like integral from 0 to n. And then what's the derivative of this guy? It turns out to be 3 over 2 root x, e to the 3 root x. I guess you can still have an e here as well. Okay, so this is just a calculus fact. I've written this as like a starting value of 1 plus the integral of its derivative. Why is that useful? Now, this implies if I take an expected value, this guy, well, I could say equal. I can say it's less than or equal to, because for the bound on this one, I'll just put the probability of E rather than having both. So less than the probability of E. You do expected value and indicator function, you get probability. Plus, now I can exchange the order. I could write expected value of this, but I can exchange the order of expected value and the integral. You may say, is this something technical like Fubini's theorem? Maybe, but actually we're doing expected value over a finite set, so I think it's not really very different. Right, so the expected value comes inside the integral. I'm going to put the 3 there as well. So 1 over 2 root x, e to the 3 root x. Yeah, then the expected value hits the indicator function and becomes the probability. I'll just multiply that. Probability m is at least x. Okay, and p. Right? So this is an upper bound we have on the expected value. So let's go back. It's just, I mean, maybe some people say that integration by parts, or it's anyway, it's just a thing. It's just a nice expression we can use to bound this guy. So what do we have? This is at most, again, we have, maybe for probability of E complement, I could write -1 plus the probability of E. Right, what's the rest? We have plus 3 to the 4 times all of this stuff. So we have plus 3 to the 4 probability of E, plus, okay, we've got 3 times 3 to the 4, so 3 to the 5, and the certain integral. Integral 0 to infinity, 1 over 2 root x, e to the 3 root x, probability n to the x. So, just a calculation or just a thing. Right, I'll get rid of our funny integral because that's done now. And now we have to think about cases, because the lemma we're trying to prove has an either and an or. So we either want to prove this or the other one. So I think what will be easiest is to say there's a case which just gives you the second one. Okay. So let's see what that is. If there exists x, such the probability m is at least x is at least e to the minus 4 root x minus 10, then one of the, because the maximum could be any one of z1, z2, z3, right? But that means there's probably at least a third that it's some zi, by pigeonhole that. So then there exists I, so the probability zi is at least x, is at least e to the minus 4 root x minus 12. And in this case, you're done. Because you remember what zi is, it's 9 times this thing. So then you just put lambda is x over 9. And you have probability, the inner product, sigma I u sigma. I should have and e in these things. Because all our things are and e. This time the inner product was at least lambda being x over 9, and we've just divided both sides by 9, is at least, well, this probability, but if I write it with lambda, then x is 9 lambda, so I have root of 9, so it comes out instead as minus 12. All I'm saying, I suppose in some way, is if the maximum is likely to be large, if, then picking an I, dividing by 3, one of them is likely to be large, and you could translate that to the inner product, just dividing by 9 in the appropriate way. That's all we did. It's because x is 9 lambda, and so you have 4 square root of 9 lambda, but the square root of 9 is 3, so it comes out. So if this thing occurred, then we're just done the geometric lemma because we have this second case. So we may assume that in fact this is not the case. For all x, in particular for all x positive, the probability, the maximum is at least x, and e, whatever, is at most e to the minus 4 root x minus 10. Good. Because now we wipe that into our integral. See, this is at most we've got minus 1 plus 82 probability of E plus. Right, what happens here? We've got a 3 to the 5. we're whacking in our upper bound on this guy now, because we can assume we have an upper bound. I guess I should have carried through to here and D. If we have an upper bound on the probability of e to the minus 4 root x minus 10, I just whack it in here. The e to the minus 10 I'll pull out in front. E to the minus 4x cancels the e to the 3 root x, sorry, e to the minus 4 root x, yeah, it cancels the e to the 3 root x, and even leaves you with an e to the minus. So you just have the integral 1 over 2 root x e to the minus root x. And don't all shout out at once. What's the value of the integral? Value of the integral is 1. You just need to calculate the derivative of e to the minus root x and stuff. The thing is like a trick to calculate an integral over an interval is that if this is the derivative of e to the minus root x, or minus half, whatever it is, and therefore you can evaluate it. Good, so that's exercise in differentiation of e to the minus root x. But with that in mind, we've actually completed the proof because what we now have, you can put 1 on the other side, and we have 82 probability of E. Well, this is 1, this is at most a 10th, plus a 10th is at least 1. Well, that means 82 probability of E is at least 9/10. That means probability of E is at least whatever. I don't know if that's the right way to think about the proof. I mean, you often give the proof. You should. I think maybe the way you should think about the proof is more like we want something to happen. We want E to happen, in fact, with some probability. If it doesn't happen, we have a very, very large, probability very close to 1 that we're getting -1. Well, that means because our expected value of the whole world is positive, not negative, there's something to offset this bit which is like -1. Something to balance it. But where does it have to come from? It has to come from these guys, the positive bit, and you're going to need enough value on high enough values in order to rebalance. You're going to have to give enough probability to large enough values in order to get to positive again. And when you do the calculations, basically this is what you get. I guess that's another way to say the story, but I don't know if it's, anyway, there you go. Yeah, in a sense it's a technical thing, right? But it's a nice thing. It's a nice thing. So yes, some people might say, well, it's a slightly strange looking statement. Either you get what you really want, which is all of the at least -1, or we sometimes call it a cap-like behavior. It's really like a cap. If you thought of points as being on some sphere, then cap-like behavior is lots of them bunching up near each other, which would be like surprisingly large inner products. And so in a sense, it's a result of that type. Either you get what you want. Did I attempt it? Let's do 100. Yeah. It's supposed to be 100. Right.
This is corrected for you people.
Is that right? Oh, I see. I'm my own worst enemy. Right. So either you get what you really want, or somehow the inner products are bunched up somewhere. I think when I saw Julian speak about this, and there was one of the questions I think towards the end was asking, but it's a weird, this statement is sort of scale free. You can choose the functions however you like, you can put them however you like. If you make you could map points to the points of a simplex in high dimensions, and then all of the inner products are negative, right? And you can just blow up the points to be further and further away, and you can make the negative inner products as big as you like, and it looks like it would be a contradiction of the lemma, right? But what happens is that if you're making points bigger as you're multiplying, you also make it easier for this to happen, right? You also make it easier for them to be bigger than a certain lambda. And if you do it with few points, which is another way that you can get larger negative inner products by having fewer points, then you risk there being a decent probability that these two are actually equal. If you do a few points, or you could be mapping all the points of S just like 10 points. But then you have a decent probability that you actually choose the same point. And that would count as a very good product. So in some sense, yeah, this seems to work, and there isn't some silly counterexample just about scale. Okay, so I've cleared the board. We can now state what I'm going to call the key lemma, which is basically the geometric lemma but translated back to our language graphs. And then we can define our actual algorithm that we hope to use to find. Just to set up a little bit of notation, we recall we're going to be building books like this. And these would all have to be the same color. Click here. And what was very important for the future steps is to maintain good density, or in fact, the minimum degree from X to these sets in the respective colors. So we're going to use PI is the minimum degree condition you have between X and YI in color I. In other words, it's the minimum of the number of neighbors X has in color I in set YI, always normalized by the size of that set. So if I have P equals a third, that means every vertex in X joins to at least a third of that. But P is a half, will be every vertex in X joins to at least half. And this is the thing we're going to try and maintain and not make it too small during the proof. So let's state the key lemma. And what will happen is, as you look at the key lemma, you may feel it's not the same as the geometric lemma, but they say like history doesn't repeat itself, but it rhymes or something. It kind of feels a bit like the key lemma, the geometric lemma. And indeed, next time you'll see this does follow relatively easily from the geometric lemma. So I'm going to put it in our context where we have X and Y1, Y2, Y3. Disjoint sets, and let's see color the edges of the union of these sets. Then you can make any sequence, alpha 1, alpha 2, alpha 3 positive. These have to do with how much density you're willing to lose, or minimum degree you're willing to lose in a given step, but in principle, for this lab, they can be anything. Okay. And what can we find? And we can always find then there exists a vertex X in X. There exists a color, which is 1, 2, or 3. There exists a subset, X prime of X. and a subset yi primed of yi, just for this one I, such that, so you should think of these as the subsets we're going to update to in the next step. Right? You're going to be able to find the vertex x, which you can use by putting up here, restricting to x prime and to y prime. Well, there are actually going to be two cases. One of them corresponds to the case that you do want to do a color step, where you do want to put x in T1 here and restrict x and y1. There'll be a second case which corresponds to the density boost step. But the first thing is properties y are actually always true. We're always going to have that with yi primed as size given by the previous mean degree condition between x and yi times the set of yi, basically because it's the size of neighborhoods. And the other part would be that actually you choose this yi primed in the neighborhood of x in the right color. So I'm sort of saying there'll be a way to choose the vertex in here and a way to choose the color so that well, x prime would be like his colors in neighbor right here, or it actually could be a different thing anyway. Y primed would be like his neighbors up here. And we've got one more information. Either, again, we have two cases, as we did in the geometric lemma. The first case is that you're going to do, it's kind of the one where you want to do a color step, which is the one where your mean degree condition may go down, but not too much. And what you have is x primed is also contained in the appropriate neighborhood of x, because x has been set. The size of x primed, you have a lower bound on it, which is e to the minus 2 to the 25 times the previous size of x. And here's the important bit. You don't go down too much in this mean degree condition. In other words, pi of x primed yi primed is at least the previous value between x and yi minus alpha. Or there could be something else that happens. The something else that happens is you can go into a subset where the mean degree condition will actually increase a lot. And that condition is there exists lambda at least 2 to the 42, such that your x primed has size at least e to the minus 12 root lambda minus 12 times the size of x. And now the mean degree condition will increase between x primed and yi primed is at least the pi between x and yi plus lambda alpha. You get to increase this condition by lambda times more. It's quite a lot of information, but basically, you can choose something to the left and right. The stuff to the right will always be basically the neighborhood of little x on the other side. So be the right sides. And so one of two things happen. Either you don't go down too much in the left, and you don't lose too much of this sort of density degree. Or there's some large lambda, and if you go down a bit more in the left, you can increase the density across by quite a lot. Right? It's more than 2 to the 42 times what you're willing to do. So you're not going to do this too often, right? Because the times you do it, you go up by 2 to the 42 times what you would get at. Okay. So now we can state the PUC algorithm or library algorithm. That's the rifle name. The books. Good. So again, given x, y1, y2, y3, and 3 colouring C, what we do to start with, we know we want to build these books, and the cliques we're going to call T1, T2, T3. Of course, we start off with them being empty. And then we repeat the following steps. I suppose we repeat until either X is empty or some of one of these Ti gets up to size T. Remember, little t is there's going to be some specific multiple of k. It's going to be like 2 to the minus 30 times k or something. So either we go long enough that we find the book with enough in its clique, or if we run out of verses, we'll just stop. So what do we do repeatedly? Well, step 1 is we apply this lemma. To apply the lemma, you need to decide what values of alpha you're using. So you define your alpha I at this step, so actually you could choose a different alpha I every time. Of course, previously I think our I was indexing time. Now it's indexing one of the colours, 1, 2, or 3. But you have separate parameters at the time when we did it. But we won't bother doing it now. You just put this step alpha I as a certain value. What is it? It's the current in degree type condition you have, I guess between x and yi, minus, in fact, we never want to go below a third minus 2 delta. So you just take the difference, divide by t. This can be a choice of alpha. Apply the key lemma. Delta is going to be a very small constant, like 2 to the minus 40. Yeah. So we're not willing to lose too much. We don't lose too much. Right. So we apply the key lemma, and what do we get? We obtain little x in x, x primes, and yi primes. I suppose we obtain an I as well. We obtain all of this from that. But what we choose to do depends on which of the two cases we're in. If we're in 1, so I guess we call this 2, if the lemma produces something which corresponds to this first case, we do a colour set, which is exactly as we've been describing. We will add x to Ti. We restrict the set x to just its intersection with the neighbourhood of x in that colour. And you restrict yi to... actually, I should call this x prime, because that's what x prime is already, right? And x prime's the lemma, and x prime's contained in it. So I guess in some sense, x goes to x prime and yi goes to yi. But they both have the property in this case of being contained in brackets. So otherwise, what do? We do a boost step, which will increase the minimum degree property between x and y. So you don't add anything to any of the cliques. You just do x goes to x primes, yi goes to yi primes. So in some sense, this is useless from the point of view of actively building the book in that step. However, it gives you a better min-degree condition for the whole of the future. It's an investment. So In a way, actually, the statement of this algorithm is slightly simpler than the one from the other proof. But yeah, there's still a little bit of complexity there about, you know, what we do and where it comes from. So let me know if you have any questions. I guess like next time we can see the key lemma follows the geometric lemma maybe. It's not too difficult, but you just need to write down that you're going to use the neighborhoods to define these functions sigma 1, sigma 2, sigma 3, and then you apply the geometric lemma. Depending on one of the two cases you get from there, you get one of these two results. Okay, so I guess that for now. This next week we'll certainly do that, and then it'll probably be in the next two classes. We'll also be able to do all the remaining details of proof. Okay.